Here's an example of what significance testing would look like in the presence of one of the web apps, so we don't have to pay attention to so many details computationally along the way. So in this problem, we're talking about a survey of 1,000 randomly selected American women in a certain age group that where we asked what medical condition they feared the most, and 530 said cancer. In some problems, they would say here, instead of saying 530 said cancer, they might say 53% said cancer. And the reason that's relevant, if they say it that way, then we have to be able to use the technology. We have to figure out how many people that was. So in this case, that's not hard, because if they told me 53% said cancer, I just have to figure out what is 53% of 1,000. But I could do that. So 53% of 1,000 would be 0.53 times 1,000, and it's pretty easy to see that ends up being 530. But if this question had, asked about, 1,700 people and said 48% said something, then we would have to do 48% of that total to figure out how many said that. You'll see why I'm pointing that out here, because the web app has a very specific way it wants the input, where it wants you to tell it the number of people who answered a certain way, not the percentage. So anyway, so this problem is given the right way around. It tells us the size of the sample. It tells us how many of them answered a certain way, and we want to be able to test a claim about the population proportion. In other words, the proportion of all American women who would answer that same way, if we could ask them all. And so that's the statement here. I will always ask you to write down the actual proportion that we're testing. So P is the proportion of all American women who would answer cancer if asked this question. And of course, we don't know, there's no way we could ever know what that P is exactly. So instead, we're asking a randomly selected sample of 1,000, and we're going to see if we can infer something about the parameter P from what the sample said. The question in the problem is asking whether we can conclude that the majority of American women would answer this way. So saying the majority would answer that way is the same thing as saying that the parameter P, the population parameter P, is greater than 50%. So greater than 50% is what it means to be the majority. We know that that form would only be suitable for what we call our alternative hypothesis. Our null hypothesis is always an equal statement. And so the null hypothesis here would be that P is equal to 50%. And so that's the situation we're in, where we have a null hypothesis, that's a statement about P being equal to some value, and an alternative hypothesis, which is often the claim that we're trying to test. Usually, in most scientific studies, the P would be a not equal to statement. The alternative hypothesis would be a not equal to statement, just so that there's no bias going into the study. But in this case, it specifically asks about majority, so that means greater than 50%. Okay, so the first thing we do is, under the assumption that the null hypothesis is true, so the null hypothesis being true means that we know that the true value of P is 50%. And what I always want you to do is draw a picture of what the sampling distribution would look like under that assumption. If the null hypothesis is true, then our sampling distribution, or we call this our p-hat distribution, is going to be centered at the true value of P. So that true value of P is coming from the null hypothesis. That is what, that's the result of assuming the null hypothesis is true. To label the tick marks, I need to stop and figure out standard error. So the standard error formula, if you remember, is do the square root of we don't know the P, so we would use P hat instead. P hat times 1 minus P hat divided by the sample size. So that's 0.53 times 1 minus 0.53 divided by 1,000, and then we take the square root of that answer. And in this case, that ends up being about 0.016. That's 3 decimal places. So on my sampling distribution, I know that every tick mark would be 0.056. So let me just label 1 in each direction because there's too many decimal places here. So if I add 0.016 to 0.5, I would get that. If I subtract 0.016 from 0.5, I get 0.84. So you could label a couple of them if you want to, but that's just 1 tick mark in either direction, just to give me a sense of the scale. Now I want to mark on this graph, I'm going to mark the particular sample proportion that I collected. So when I really did this study, 530 out of 1,000 answered cancer to this question. And so that's 0.53. So 0.53, if I had drawn another, let me use a different color. So 0.53 is going to be about right there. If you would label that second tick mark, you'd see that this line is a little bit short of that second tick mark. If you're not 100% sure where that line is with respect to the tick mark, that's one good thing that the z-score is for. The z-score, if you remember, is the observed value that we, or the value that we observed, 0.53, minus the mean, and I'm talking about the picture that I have on the right there. So the mean of that picture is 0.5, and the standard deviation in that picture is 0.016. So if I do that calculation, I'll get approximately 1.9 as my z-score, which means I'm not quite to the second tick mark. And if you look at my picture where I drew the 0.53, that's about right. So I'm past the first tick mark, not quite to the second tick mark. That's what the z-score tells us, is which tick mark you're close to. All right, so that's the picture, that's the situation of putting together the statement that the null hypothesis is true. That's what gave me the picture in the first place. And then the data that I collected is that red mark that I wrote on there. So what I've done is I've combined the null hypothesis being true assumption with the actual data that I collected, 0.53. And so what we're trying to measure with p-value is we're trying to measure how unusual those two things are for each other. In other words, how compatible are those two things. Because our alternative hypothesis has a greater than symbol in it, then in my picture, I would have the labeling to the right is going to be, I'm going to shade the area to the right of the line only, because it's a one-tailed test with a greater than sign. And the area of that I've shaded is exactly what I mean by p-value. And so this is the thing that we would normally go to our z-table. We could look something up. We could do all kinds of stuff. But if we're going to use technology anyway, we don't really need to do that. Let the computer do those calculations for us. So now that I have an idea of how it would all be set up, here's what it would look like to be putting it into the computer. Notice how in the setup here, this is what I was talking about before. The input for the computer program is the sample size and the number of successes in that sample size. So successes here just means the number of times people answered the way you're paying attention to. So for us, the people who answered cancer would be considered a success. So knowing that it was 530 out of 1,000 is actually what we need to know for the computer program. That's why I was saying if they had just told me 53%, I would have to figure out how many people that was in order to be able to set this up. I click this box, select labels for success and failure. It allows you to put in some things here just so that it doesn't, so the picture makes more sense to you. It's totally optional. There's no reason to do that in terms of the numbers. The other part of the setup, it's important, is telling it that we're doing a significance test. The other option here is a confidence interval, and the confidence interval is not going to tell us what we want to know. And then finally, here's where we're telling it our hypotheses. So ironically, we'll do that last in this box, even though that's the first thing we set up in our process. So this putting 0.5 here means that my null hypothesis was p equals 0.5. The alternative saying greater, it just means that in the alternative hypothesis, there's a greater than symbol. Your choices there are greater, less, or not equal to. So those are the only things that we've ever seen in an HA statement. And so that's it. We put all those things in. I'm going to go to the next page so you can see what the output looks like. Here's a screenshot of the output of the web app. You can see over here on the left all the stuff that I had showed on the front page. But now we can see the output. And you'll see in the output there's a lot of stuff that we could have saved ourselves some work by just doing this earlier. For example, here is the standard error. They call it the null standard error. What they mean by that is it's the standard error in that picture, assuming the null hypothesis is true. The test statistic, the z-score, is right there. I rounded mine off to 1.90, but you can see they wrote out the whole thing there. So, so these two guys are numbers that we had to compute on the other side of the, well, earlier in the process. And then, of course, this is our p. That's our p hat. So all of those calculations that happen on the front side, I keep saying front side. I know a PDF only has one side. But anyway, on my piece of paper, it's the front side. All of those numbers that we calculated are all part of the output for this. We can see that the picture of this distribution matches what we drew. You'll notice that it's giving you the standard normal distribution. In other words, this is the z-score distribution, which wasn't really what we drew in terms of the labels, but we can see that the mark on the thing is just short of the second tick mark, and the shading is to the right. So as far as the shading goes, this is exactly the same as what we drew. And finally, we can see here the actual p-value. And so that's what my takeaway is from the point of view of the significance test. My p-value is 0.0289. So now I can write a conclusion, and I have a technical conclusion first, which is since this p-value is small, and remember small here means less than my significance level. My significance level in this problem, which we usually write alpha, is also given in the problem. If you look back in the problem statement, the 0.055% is given there. So since the p-value is small, we always say we reject the null hypothesis. That's our technical conclusion. And then in English, we say that we do have evidence to support, and then I'm going to write as best I can the statement HA. So what goes in the blank is always the statement HA. Rejecting H0 means I'm supporting HA. HA in this case, remember, was that the majority of women would have answered this way. So p greater than 0.5, the way they said that in the original problem was the majority of American women, at least in this age demographic, would have answered this survey question with cancer. So that's exactly what p greater than 0.5 means in words. So I have a nice statement. This study provides me enough evidence to conclude that the majority of American women would answer this question, cancer, if we could ask them all.